So this video is going to be talking about glucose metabolism specifically in the liver and what gets regulated in which way during exercise. So we're going to be talking about chiefly gluconeogenesis, which is the creation of glucose from non-glucose intermediates, which are highlighted in green, mainly glycerol, lactate, and amino acids. The job of the liver during exercise is to put glucose out into the blood. This is called hepatic glucose production output, and it's signified up here where we see our single glucose molecule, and then this arrow is signifying it leaving the liver and entering the bloodstream. So what we see here is a pathway on this side, which is glycolysis. And it would take this glucose molecule and, through a series of reactions, convert it down to pyruvate, which would then get oxidized into ATP and reducing equivalents. And then on the right side of this, we would have the opposite, and it would be a series of reactions that would formulate a glucose molecule, and that would be gluconeogenesis. So let's begin with our familiar exercise hormones, epinephrine and glucagon here, and of course they work through secondary messenger cyclic AMP, shown here. So cyclic AMP will activate glycogenolysis to break down liver glycogen, turn it into glucose 6-phosphate, which can then be turned into glucose and put out into the blood. Cyclic AMP through epinephrine and glucagon will also act on this key rate-limiting step of gluconeogenesis, which is again producing a glucose molecule. It acts on the enzyme called fructose 2,6-bisphosphatase, which catalyzes this reaction here in the direction of creating a glucose molecule. So we have exercise activating glycogen breakdown and activating gluconeogenesis, which are two ways to increase the amount of glucose that the liver can output into the blood. We also have an inhibition caused by cyclic AMP, and this would be on pyruvate kinase, and it will actually act to inhibit this reaction, because what this reaction is doing is it is a terminal step in glycolysis. So if we inhibit the direction of glycolysis, which would be glucose oxidation, then we will accumulate glucose within the liver. This could be a little counterintuitive in that during exercise we want to oxidize glucose for fuel. However, we are in the liver here and not in the muscle. So the liver's chief role during exercise is to output glucose up here. So we don't want to be pulling glucose through glycolysis and start oxidizing it on the spot in the liver, because that would provide less glucose for it to put out into the blood and get to the muscle where it needs to be during exercise. Over on the right hand side here, we have our exercise hormones, epinephrine and glucagon, and here, through cyclic AMP, we can see it activating a enzyme called PepCK. PepCK catalyzes the reaction of oxaloacetate into phosphoenol pyruvate, which can then enter the gluconeogenesis series of reactions and form more glucose. So we see exercise hormones upregulating PepCK. This is just another arm of exercise that can increase gluconeogenesis. It's basically doing the same thing as cyclic AMP is up here, except it's just targeting another rate-limiting step of gluconeogenesis. So just to orient ourselves here, oxaloacetate can come from pyruvate, which comes from lactate, or amino acids, which are just non-glucose metabolites to produce glucose. So it's just gluconeogenesis. And then also on the side, we have epinephrine and glucagon, and through cyclic AMP again, it's working to inhibit phosphofructokinase, which is an enzyme that will catalyze this reaction again, however in the glycolytic direction. So it's going to inhibit an enzyme that's going to pull this glucose down into the oxidative pathway. So again, we have arms from exercise hormones that are going to be inhibiting glycolysis here and here, and we have arms that are going to be activating gluconeogenesis here and here, and the total compounding effect is going to be an increase in glucose that is available to be output by the liver into the blood. Acting to also increase glucose to put out into the blood will be cyclic AMP on glycogenolysis. However, this is separate from the whole gluconeogenesis and glycolysis pathways. An important note about gluconeogenesis and the liver and exercise is that as you exercise, you accumulate these metabolites in the blood. Therefore, as you exercise further and further, gluconeogenesis becomes more and more important into the role of hepatic glucose output. Furthermore, post-exercise, as the blood flow shifts from the muscles back to your internal organs, including the liver, you're going to get an increase in blood flow and blood that's chock full of metabolites that have accumulated during exercise, and it's going to be rushing into the liver. So all of this is going to be super upregulated, and it's going to put out a lot of glucose in the blood, and that's great post-exercise, especially so we can replete our glycogen stores that we have depleted during exercise. So yeah, I hope that was helpful. Just a quick review again. We have exercise acting to increase gluconeogenesis here and here, which will increase the amount of glucose we have available to put out. We have exercise decreasing glucose oxidation here and here, which will increase the amount of glucose we have to put out. And we have exercise increasing glycogenolysis, which will increase the amount of glucose we have to put out.